On the other hand, and regarding the elevation plane, here cones geometry determines the shape of the radiation pattern. Let's say that the wider the flare angle is, the wider the radiation pattern is. Therefore, less gain. As you can see here, the blue curve, okay, this is how the radiation pattern on the elevation plane is, and we are able to change, okay, the width and also the beam width of this radiation pattern, playing with the geometry of our cones, for example this angle and this angle. So a general rule would be that the wider the flare angle, the wider radiation pattern. Okay, this is the most common rule for this geometry. Okay, so antenna matching S11, an important point. So focus here guys. So first of all, a typical figure of merits of an antenna's matching is S11 parameter. As you can see here, this is a classical behavior, a classical figure of an S11, a good S11 parameters of an antenna. What do we want here? Well, as you may saw in other courses, here what we want is to have an S11 below -10 or below, ideally, -15 at the whole frequency band. For example, here this antenna was from 2 up to 6 gigahertz and presents a good matching, as you can see, all the way below -15 dBs. Okay, so secondly, and regarding the impedance, we got to say two things. So the first one, input impedance of a biconical antenna behave similar as a dipole antenna. Therefore, the input impedance equation looks like this. We got a real part and then we got a imaginary part, which is the reactance part, okay, the reactance effect, which could be inductance effect or capacitance effect, depending on the sign. Okay, so there are two ways to compensate the default inductance presented on the input impedance. Here we got the inductance, and we want to compensate, to eliminate this effect in order to have just the real part, which should be 50 or 75. As you can see here, these are common input impedance in almost all those systems. So for that, to compensate that, we got two ways: to introducing a shortening factor on the length of a dipole, for example, or enlarging the cross section of those dipoles, which is the way how we get cones. So a real example of the first case, the first way to compensate that is, this is a real example. A λ/2 dipole presents this input impedance with the real part and the inductance part. So introducing a shortening factor on the length, for example, reducing the length to those values, this is a good way to reduce the inductance factor. In other words, if we introduce a shortening factor, we increase the capacitance effect, which decrease the inductance effect, in order to get the real part. Okay, just this value is what we want to get. And why do we want to reduce this part, and why do we want to get this value? Well, basically because the cable which feed our antenna will present a real input impedance, which should be equals to this real value. So as it is said in this point, input impedance, to avoid reflected power at the input port of the antenna, the input impedance must be equal, okay, to the characteristic impedance of the coaxial cable. Commercially, typically 50 or 55. As you can see here, this value is really close to this value. So compensating this effect, we match the input impedance of our antenna to the characteristic impedance of the cable which feed it. So this is all regarding S11 impedance matching. Okay, so remember, this is important. Sign positive means inductance effects, and negative sign means capacitance effect. Okay, so let's move on to effect of cones geometry. So first of all, here we got a clear relation between the flare angle and the input impedance. So if we want to match your antenna on a specific frequency band, you got to play with this angle. Okay, you got to optimize this angle for this particular frequency band. So secondly, remember, talk about cones is the same as talking about wideband dipoles. Okay, and for that wideband effect, you should use the angle flare over 2 should be between 30 and 60 degrees. Okay, that's for wideband application. Remember that. So thirdly, according to the resistance and reactance figures, the flare and the length of cones can be obtained. In this way, a broadband biconical antenna could be achieved. So let's go. Let's see, what do we got here? Remember, the real part of the previous equation, the input impedance equation. Here we want to get the real value. Okay, we want to obtain 75 or 50. So for that, this is the value. Imagine that we are going to use 50, so should be around here. Okay, let's trace a line, for example, and there we go, this area. Okay, so if we select this value, let's say 160, for example. Okay, if we move to 160, this is what we get. Remember, 160, and then select this curve. As you can see, there is a value here for the flare, for example 80. Okay, 80. 90, let's say 90, this curve 90 at the flare angle, and 160. Okay, keep in your mind those values. So here we to the rectance figure 160 over here, and then let's find the 90. There we go, 90 is over there. And as you can see here, if we select this graph, these dimensions, we obtain a zero reactance effect, which is what we want, and we obtain a 50 real part ohms, which is actually what we want. So that's how you define your dimension, you know, preliminary in a gross way. Okay, this is a good way to make your first approximations in terms of parameters, in terms of your dimensions, the geometry of your cones.